Okay, so now to wrap up this section, let's look at these two systems of equations here. Notice how the left side is the same for both systems, but now we're looking at the right side is different. Up until this point, remember the four squares in the previous video, where we were looking at the dimension on the top, right? We said, okay, if we look at the left side of the matrix, right? We're talking about the augmented matrix. We look at the right side, or excuse me, if we ignore the right side and look at the left side, then the associated homogeneous system, we will then be able to see whether there's a unique solution or infinitely many solutions, right? For the general case. Now, we haven't talked about the other dimension where whether a particular solution exists or not. That's the tougher one to deal with, okay? So if we look at this example here, notice how the left side is the same and the right side is different. This has a unique solution, or excuse me, this solution exists, this one does not, okay? And so you might think, well, okay, so that means that we can use the right side to determine whether a solution exists or not, and use the left side to tell us whether the solution is unique or whether there's infinitely many solutions. Now that conjecture would be incorrect because I can just give you another example of where that does not hold, because I can say, oh, how do I want to do this? Oh, so I can change this to something like this, and I'll change this to 4. Yeah, that'll work. So now in this case here, the first one has a solution and the second one does not. So this one has a solution, the second one does not. So even though now the right side is the same and the left side is different. So what's going on here? So we know that the right side, obviously from this, the right side alone does not determine whether a solution exists or not. And what we find out is that it's really depends on some interaction between the left and the right side. Now, if we look at a system, and let's look at this one here, and let's use some intuition to kind of help us here. So let's use this example here. Oops. Okay, now if we look at this system of equations, and we're going to use where we have a system and this c is a constant, this coefficient c is unknown, okay, so we can make that anything we want, okay. Now, if c is equal to 2, the system has no solution. And you could see that this is the case because if you add up the left side, these two, if this is 2, right? then if you add up the two equations on the left, you get the third row. While if you add up the right side, you don't get the third row. And so there's your contradiction, right? So there's no solution to that one. Okay? But if C is not equal to 2, then there is a unique solution. For example, let's do 1. Okay? Okay? You can find it that there is a solution. So for a system to have a solution, if one row of the matrix of coefficients on the left side is a linear combination of the other rows, then on the right side, the constant from that row must be the same combination of constants from the same rows. So if you look here, let's see here. Let me see. Yeah. Yeah, so for a system to have a solution, if one row of the matrix of coefficients on the left side is a linear combination of the other rows, then on the right, the constant from the row must be the same combination of constants in the other row. Okay, so that's what we're going to leave it at. We're going to get more into this later on in the next chapter, but this gives you an idea of how we're going to approach when there's a particular, whether a solution exists or not. Okay, and we're going to talk about linear combinations, and that's going to come to the forefront, and it's going to be very important. One of the things we're going to look at is looking for situations where one row is a linear combination of all the other rows. And we'll leave it at that. Have a great day.